We have reactions that suffer from rearrangements, and we need to be able to recognize the reactions that are going to go through a rearrangement. So let's go ahead and do this one right here. First, we protonate because we need to see the intermediate carbocation and check whether it's going to rearrange or not. So when you add the hydrogen, we're going to add it to carbon number 1. The positive charge will go to the second carbon. So this particular protonation will get us a secondary carbocation. I had 2 hydrogens, I added 1 more, so now I have 3. And the positive charge is right here. This is a secondary carbocations, and although they're stable, tertiary carbocations are a little bit more stable. So this carbocation is going to check what can be moved so that it can be tertiary. And next to it, on the left side, we have a carbon that happens to have 3 methyl groups attached to it. They don't need to be methyls, but in this one, this is the example I have here. So if you were to classify that carbon, that would actually be a quaternary carbocation. The carbon is attached to 4 carbons. And whenever you have a quaternary carbocation, we will move the smallest group attached to that carbon, which happens to be a methyl. So what I'm going to do is I'm going to put a little piece of paper right here to show you what's happening. This carbocation is going to ask for some electron density from the neighbor on the left, and it's going to get the best donation ever. The methyl is going to basically move from one carbon to where the positive charge is, so it comes, poops, and it moves to the other carbon, and the positive charge moves to the carbon that donated, the CH3. So if we have that rearrangement, now we're going to have the positive charge on the left carbon. Now remember, that carbon just lost one of the methyls, but it's now a much more stable tertiary carbocation. This is what we call a methyl shift because we moved a methyl, but generally you always move the smallest thing attached to the neighbor. So for example, let's do the exact, it's the same starting material, but the neighbor now has 2 methyls and a hydrogen attached to it. So let me real quick draw the carbocation. And if I am to move the smallest group attached to this neighbor, what would it be? It would be the hydrogen. So that's the smallest group, and it takes less energy to move the smallest group. So if I was to get a little new piece of paper right here, again, there's a hydrogen right there. It's just going to move next door. So I'm going to disconnect that hydrogen and move it to the carbon that has the positive charge. The positive charge will move to the left. It's an exchange. So if you move the hydrogen to the right, the positive charge moves to the left. Now this particular rearrangement is not going to be called a hydrogen shift. The correct name for it is a hydride shift, because when we move that hydrogen, we move this right here. That's a hydrogen with the 2 electrons that it had in the bond, so it's a negative, and a negative hydrogen is called a hydride. So this rearrangement we did here to get the tertiary carbocation is a hydride shift. Now, when do you get the hydride or the methyl shift? Well, check your carbocation and what neighbors do they have. This one at the bottom was a tertiary carbon. The one at the top was quaternary. So that gives you a clue, something is better than secondary. And you always move the smallest group. If the smallest group is a hydrogen, you'll get a hydride shift. If the smallest group is a methyl, you'll get a methyl shift. It doesn't need to be a methyl. If you move an ethyl, then it would be an ethyl shift.